Hi, Professor Jeff Sexton, and I'm going to walk through the literacy sheet for PSLM.05, normal and exponential functions here. So first off, I'll probably do this in a couple videos, so for fair warning, apologies on the lighting, it's early morning here on the East Coast. So first we're asked to go through two normal cumulative distribution functions, and we're asked to identify which one was which. We know that the one with the larger sigma, or standard deviation rather, will be the more elongated function, and then the one with the short standard deviation will be the quickly rising, oh sorry, that was way off, the quickly rising function here for you. So you do have that advantage. Ooh, we can zoom in. So there's your shorter standard deviation. Most of the terms are going to be right around the median, and then here's your larger standard deviation, more spread out across the graph. Let's see now. We were then asked to show what happens here if we have the same normal cumulative distribution graph here, but we have two different inputs. What happened and why were they exactly the same? And we know that when we go ahead and change the format of the inputs and take the x out of the equation, so it's no longer x plus m or x m and sigma in that equation, when we take out that x and we put in m plus s sigma, that's going to be flushing out, as we've termed it in our homework books, the x from that equation, putting in the m plus s sigma, which is going to take out the references of the mu and sigma, which will then give us a more standard graph, which is going to be equal, flushing out that x variable out of that graph itself. We were then asked to go ahead, I'm trying to keep this in focus for you, which is why I'm moving it a little bit more, asked to go ahead and see two different graphs, a normal cumulative distribution, which is this dark heavy line here, ending at the 1, and then also the exponential rather, excuse me, again ending at 1. Here's your exponential graph, is that large looping graph. Here is your normal cumulative distribution as it grows and all the data accumulates up until you get 100% of the data all the way at the very, very end. Bell curves. Bell plots, here we go. The smaller sigma is going to be where all the data is concentrated in this very high rising graph. A larger sigma is going to signify more of a spread out of all of that data across the graph. So that's which one is bigger, the more spread out. The dark curve is going to be the bigger sigma. Here are two more bell plots, and we've been asked to go ahead and find out. We've been asked to find out which median was bigger. We know, getting back to this one, that the median here at 10 is going to be bigger than the median here. It's probably around 6, I would have to estimate. Then we're asked to ask about standard deviation, which one is bigger. We do know that all of the concentrated data is going to be here, and this one's going to be, again, spread out more, so that sigma is going to be a little bit bigger on this light graph here on the left-hand side of this graph here. Going forward, we do have another one, and it's been shaded for us. So what does this mean? What did we get ourselves into here? Let's kind of bring it up. So we have all this data given to us. We know our medians. We know our standard deviations. Do we know our standard deviations? I don't know if we do. No, we don't. But we know that these graphs have been taken out to 2 standard deviations left and right. In spite of not knowing what the specific values of the standard deviations are, how do the two area measurements are related? We both know that they're going to be 2 standard deviations away from the median, so you can see that there's a little bit of data here that's not contained. That's because most of the data is going to be within two standard deviations, but not all of it. So we do know that we're calculating from 2 standard deviations, so from the median, 2 standard deviations over, but not all the data is going to be encompassed in that, so that's why you don't have it there. You can always go out 3, 4, 5, 6, 7, 10 standard deviations, and it's just going to be a really minuscule amount of data that's going to be left, especially when you get outside of 4 standard deviations for sure. All right. Now, getting into the relationship between normal community distribution and the bell curve. So we were given this awesome graph here that also has a bell curve and a normal community distribution function in it. We are asked to go ahead and show how that formula is going to be changed from normal cumulative distribution into a bell curve function. And we learned in one of our homework sections here, I'll kind of zoom in here, that when we went ahead and had our normal community distribution really broken out into that large format here, if we change the n+1 here, and we also changed the exponent n+1, and then we took out one of these halves, we then had a modified function here. And we knew this modified function, when we put it into our graph, it came out as a bell curve, and that was very interesting. So then we go in here, and actually if you clean up this function and go ahead and combine these terms in, this is what you're going to get here. And this is actually your bell curve function. This modified function and this bell curve function are actually the same function, just kind of flipped around a little bit for you. So we do know that from the normal cumulative distribution, by changing the n+1 to sigma and changing the 2n+1 to 2n here, and then taking out that half, making those three little tweaks to the system here, we're then taking this out, putting sigma in, and we're actually creating that bell curve function that we're able to use, which is pretty interesting. It's a pretty neat trick there. And then we are asked to say, I also wanted to put in here, we've been using, since the normal community distribution function is a polynomial function, and this is going to be an exponential function on the bell curve side of things. We've been using k=40, so that's going to be a large chunk of information, so that the degree of the polynomial is going to be 20, so that's 40k. So that's going to be a large enough or most expanded out. That's going to give us an accurate representation of an exponential function like the bell curve plot itself. We can always up that k, but as we saw in our homeworks, that 40 number really gives us a really nice view. When you take out that normal community distribution function out to k=40, it gives us something very similar to what the bell curve looks like, and it's pretty useful in calculations. So that's what we've been using. Finally on this video, before I wrap up and go into the next video, we were asked, why does the normal community distribution curve level out, and the bell curve levels out close to the x-axis? So as we've shown before, the normal community distribution, as all data approaches completion and if all the data comes in, it's going to go to 1. And then we know the bell curve here is going to be showing the data in relation to the x-axis. So when you get out here, that means all the data is gone. There's no more data represented here at the very far corner here. But then there's a little bit of data, more, until you hit that median. This is where most of the data is going to be lying in, and then less, so you have no more data on the other side of here. So those are the two differences between those functions. This one's counting up, this one's kind of showing where that data lies in proportion. I'll end this one here, and I'll start back up at L5 on the second video.